Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one is about suspended objects and the use of the centre of mass to determine how the equilibrium is reached. Let's begin with a suspended object. We're thinking of a piece of card, in this case suspended from the point A. So the object is suspended from a point so that it's free to rest in equilibrium, and we consider its equilibrium. Now if the object is suspended freely at A like that, a piece of card, you'd expect it to swing to something like that position. So how can we determine, say, what the angle, the sloping edge, which I'm indicating with an arrow, how can we determine the angle that sloping edge makes with the vertical? Well, first of all, let's go back to square one and look at the first figure on the left. Where's the centre of mass? I guess it's going to be somewhere about there. That's a guess. We know how to work that out, but let's say we've done it. It's there. Now when you suspend the object, and here's a diagram, a third diagram, it's suspended from the point A and it takes up a position hanging below. Let's say that G is there. Now what about forces? There'll be the weight acting at G, call it W. There'll be the weight acting at A, because by resolution those forces must be equal and opposite. So you have two equal vertical forces. Now if you were to take moments about A, then you would find that the force W which acts at A has no moment, but the force W which acts at G certainly does. And that means we've got a situation where the moments are not zero. So it can't be in equilibrium. The only way we can make it be in equilibrium is to move G across so that it lies vertically below A. In that position, then if you take moments about A, both forces have zero moment and you've got what you want for equilibrium. So that argument tells us that the shape which we see in the middle figure, the one with my arrow at the side, the shape will take up a position so that its centre of mass is vertically below A. So if we put it in so that that's the case, let's say that that's my guessed position, we can use trigonometry using that right angle triangle. That's meant to be a straight line. Using that right angle triangle to find that angle alpha between the sloping edge and the vertical. So let's do that. Here's a particular case. So its measurements are in centimetres. It's suspended from the same point A. So we need to find its centre of mass. So let's set it up to do that. There's a coordinate system. Here's we introduce k kilograms per square centimetre for the density per unit area, so that we can turn area into mass. And here's a table. Now what are P, Q and R? Well, I'm going to divide it up by putting a horizontal line there so that this is P and this is Q down as far as another horizontal line, and the bottom bit is R. Now the centre of mass of P is going to be where the diagonals cross. I'll put a dot there where the diagonals cross. So that would be for P 1.5 to the right from the origin, and it will be 4.5 up. So that will be the centre of mass of P. Now for Q, we'll expect it to be 0.5 to the right and 2.5 up. And for R, finally, we'd expect it to be 2 to the right and 0.5 up. Now what about the mass? Well, we work out the area. For P, the area is 3 square centimetres, so we get 3k kilograms. Similarly for Q, that's also 3k kilograms, and for the final one, 4k. R has mass 4k kilograms. So doing the usual calculations, 3 times 1.5 gives us 4.5 k. 3 times 4.5 gives us 13.5, and then again the k. 3 times 0.5 is 1.5, again with the k. 3 times 2.5 is 7.5, again with the k. And 4 times 0.5 is 2. 4 times 2 is 8, I should say, 8k, and 4 times 0.5 is 2k. So if we do the adding up, 23k is the total at the end, 4.56, 14k for the MIXI, and 10k for the total mass of the object. So in the usual way then, x bar will be 14k divided by 10k, which means it's at 1.4. Y bar is equal to 23k divided by 10k, which means it's at 2.3. So I said it was about there, didn't I? So that's perhaps just ever so slightly on the low side. But 1.4, 2.3 will be the coordinates of the centre of mass. So there are the figures in a tidier version, and we can give the answer is the centre of mass with that coordinate system. Really, I suppose I should have put an O there. Is 1.4 centimetres, 2.3 centimetres. Right, well now that enables us to work out that angle. Let's look at how that is going to work out. We've got an angle vertical. We suspend it so that the centre of mass is vertically below A, and we get an angle. So if we imagine that over here, we now know that we have the appropriate dimensions. We've got the 1.4 from the left, so that's 1.4, and it's 2.3 up, so this distance will be 2.7. So our angle alpha will have its tangent will be 1.4 divided by 2.7, and that now is the point to reach for the calculator. So there we are, a slightly neater version, and we get 27.4 degrees etc. for the answer, rounded to 27.4. So now we can answer the question. It makes an angle 27.4 degrees with that vertical edge. Well, that brings this presentation to an end. The next one is about sliding and toppling.